Okay, you guys have already learned about the general idea of work. Work being a transfer of energy into or out of a system. And today's lesson is going to be about how to calculate work. So, a couple of things. First is if we graphed, like say we pulled something across the floor with some force and it went through some displacement and we graph that, the area under that graph is the work. So we have work is equal to force times displacement. It's just a little bit more complicated than that though. There's also a times cos theta thing here. And that comes into play when you have, like, say you're pulling this direction. So you're pulling some vector that direction, but it's actually traveling that direction. So like maybe you're pulling on a rope on a crate or something like this. And there's an angle theta. So that's what this cos theta is. Theta is the angle between pulling direction, or force, I guess we should say force direction, and displacement. Should we say yeah, I guess so, displacement directions. Okay, the units are Newton meter, so force times distance or displacement. Force is Newton, displacement's meter, so Newton meter. And that's also a joule. Now I'm going to go through a bunch of examples to show how this works. So the first one, a box is pulled 11 meters along a level surface by rope. If the rope makes an angle with the floor of 35 degrees and the tension of the rope is 9 degrees, how much work is done? So we could do a little diagram here. Here's our box, there's a force, and it's moving this direction. So we have 90 newtons, that's displacement, that's 35 degrees. So we have work, force times displacement times cos theta, so it's 90 times 11 times cos 35. Get 90 times 11, and I get 811 joules. Or I could call it Newton meters, or I could call it a joule. It's the same. And the lesson from that is use only the component of the force that is in the direction of the displacement. So this, just looking at this force vector a little bit more carefully, that's the force vector and it's moving in this direction, we're only going to use that component of it. We don't care about that component. Okay, second example. A pineapple is held 1.2 meters above the floor for 15 seconds. How much work is done on the pineapple? So this one's a little bit surprising. Like, I think if I was to say, hey, hold this 3 kilogram pineapple for 15 seconds, you'd say, oh, I got to put a whole bunch of force on it and it's a bunch of work. But let's see what it actually is in terms of physics. So here's the force diagram. I'm going to call that FH for hand, or just hand, FG, and it's being held there. It's not moving, so these forces are balanced. F net is 0. So there's our force diagram. And we could also look at the system diagram, the bar chart. When we're analyzing forces or work, we're going to only put the object that we're analyzing in the system. So object we are analyzing in the system. Okay, so we're talking about holding a pineapple, so the pineapple is the thing we're analyzing. We're looking at the things acting on the pineapple. It's the thing we're doing a force diagram. That's the pineapple. So that's what goes in the system. Okay, it's not moving, so there's no kinetic. Say it has maybe 3 bars of gravity there, and then later on, still not moving, still 3 bars of gravity. So it's balanced already, so we don't have to do anything with work. We could say there's no work. There's no real transfer of energy in or out. We could say that. and just leave it like that. We could also say, well, you know what? A person's putting in some work from the hand, but at the same time, some work's coming out. It's from the gravity, actually. So that each work kind of corresponds to these. The hand is doing some work, and the gravity is doing some work. In total, though, there's no work. In total, there's no net force, and there's no net work. So no displacement means no work. Okay. And also we have that equation, right? Work equals force times displacement. If this is 0, then work is 0. All right. Let's try another example. This is example 3. 2 kilogram box was sliding across some ice and a person pulls on it to slow it down. It travels 3.2 meters while slowing down. The person had to pull with a force of 12 newtons. How much work does the person do on the box? So it's kind of like this thing. This thing's moving, the box is moving that way, and there's a person here, and they're pulling on a rope to slow it down. So the force is being pulled that way. So it starts with a bunch of EK, no EG. The box is the system. Ends with, say, no EK, or maybe 1, who knows. No EK, no thermal. It's on ice. So that's interesting, right? We started with 4. We ended up with 1 on this side. We have to balance it. So what we say is this: there's work coming out. That work is from the hand. It's negative. It's coming out. Work out is negative. So we can calculate that. We go work equals F times displacement. So the force was 12 newtons. The displacement is 3.2. So that's what, 36.24 or something like that. Oops. 38.4. Yeah. Okay, so we know it's supposed to be negative. It's coming out. We can also show that it's negative by looking a bit more carefully at our diagram and our equation. This is the direction of the force. That's the direction of the displacement. Even though it's being slowed down, it's still, the displacement is that way. And this is 180 degrees. So work really is supposed to be force times displacement times cos theta. So that's 12 times 3.2 times cos 180. And cos 180 is equal to negative 1. So this whole thing equals negative 38.4 joules. So you can use your intuition, this idea that, well, work's coming out of the system, so it's going to be negative. Or you could use the algebra to get the negative. So note, work can be negative if the force is acting in a direction opposite to the movement. Okay. Example 4. A 10 kilogram pumpkin is pushed horizontally 5 meters at constant velocity across the level floor with a horizontal force of 3 newtons from the hand. Only the pumpkin is in the system. Draw a force diagram. So we'll do the pumpkin here. So F of hand. It's constant velocity, so there must be some friction to keep it balanced. There's a normal force and Fg. And that's balanced. F net is equal to 0. The LOL diagram would look like this. Constant velocity, so maybe it has 2 bars EK, no EG, constant velocity, so still 2 bars of EK, no gravity. So here's an interesting thing. It says, basically we know there's friction. So you might want to say, hey, there's friction, I'm going to put some thermal here. The problem is, this is an energy of the things inside the system, and the floor is not in the system. So we can't put it there. Instead, what we're going to do is we're going to say, well, the hand is putting energy into the system, and the floor, the friction, is taking energy out. And everything has to be balanced here. So EK in is the same as EK at the beginning is the same as EK at the end. Therefore, WH has to be equal to WF in order for things to be balanced. And we'll see that when we do the calculations. We know FH is 3 newtons, and we know force of friction is equal to that, so it's also 3 newtons. So how much work is done by the hand? Work of hand so that's 3 times, how far did it go? 5? So that's 15 joules. How much work is done by friction? Well, that's force of friction times delta x. So that's -3. It's the same displacement, so it's -15 joules. And it makes sense. The work out is supposed to be negative, so that makes sense. What is the net work? 0. These add up to 0. And also we can, if the F net is 0, that's going to lead to a work net of 0. So if there is no net force, there is no net work. Okay, awesome. Let's go on. Next part, flip the page. Work energy theorem. So relating to this one here about no net force and no net work, there's something called the work energy theorem, and what it says is the net work, total net work acting on an object is equal to the change in the object's kinetic energy. So example number 4 is an example of this. Okay, so we can go through an example on this one. A 1,500 kilogram car starts at rest and accelerates from 0 to 50 meters per second. What is the net work acting on the car? So start its rest, no EG, we'll say it's just on the ground. The system is just the car, that's the object we're analyzing. Sometime later there's a whole bunch of EK. EG is still there, and it doesn't say anything about thermal, so we'll just leave that like this. Because it has to be balanced, there must be a bunch of work being transferred into the system. And we get work is equal to EK. We could say, like, we could call this a final and initial. We could go it's equal to EK final minus EK initial. It just so happens that the initial is 0. But we could do the force diagram on this as well. So the force diagram is pretty basic. The road is pushing the car forward, so this is from road. And there's a normal force up, gravity down. And we can see that F net equals F from road. Aha, so this time we do have a net force. That means we'll have a net work, and it's equal to the change in kinetic energy. So work is equal to 1/2 mv squared, 15 meters squared. Put that in the calculator. $168,000 joules. 169. Just gonna move this over a bit. So that's how you use the work energy theorem in a question like this. We could do kinematics. We could find out its acceleration maybe and do F equals ma and all that kind of stuff. But if we can calculate the change in kinetic energy, we know right away that's equal to the net work. So if you know the change in kinetic energy, you know the net work. Okay, one last problem. It's kind of like a challenge problem. So you can skip through this one if you're not feeling super confident about this stuff. It's a crate at rest. It's lifted with uniform acceleration. 3 seconds later, it's 12 meters high. So we have Fg down, and this time we have the lift force is bigger. So we have F net is equal to FL minus Fg. Okay, let's do the bar graph. So once again, like we have only the crate in the system. Starts at rest, so there's no kinetic. Maybe it starts on the ground, so no gravitational energy. Sometime later, there's some kinetic energy because it's accelerating, and sometime later, it's also gained some gravitational energy. So for all this stuff to happen, clearly some work had to come into the system, and let's say it's from a cable. So it's a cable lifting the crate. Now we already know that work is equal to delta EK, network, sorry. So the question is, what does network have to do with this cable and this EG? Like there's extra things there. So actually, to finish off this bar chart, there's actually some work coming from gravity. It's coming out. And so work net is equal to the cable minus the gravity. And that corresponds to this actually as well. The F net is equal to the lifting force of the cable subtracted by the gravitational force of the Earth. But we don't have to find these forces because we can use our work energy theorem. We can calculate the net work just by using the kinetic energy. So delta EK is equal to EK final minus initial. That's just 0, started at rest. So we need 1/2 mv squared. The thing is, we don't know the velocity, but we're given a time and a displacement. So we have to use some kinematics to get the velocity. So we know time is 3 seconds. Displacement is 12 meters. And we could use this equation. Delta x is 1/2 v minus v naught times t. V naught 0. So we get v is equal to 2 times delta x divided by t. That's 12 divided by 3. This is 8 meters per second. Therefore, work is equal to delta EK, which is 1/2 times 900 kilograms times 8 meters per second squared. And I did that calculation earlier, but just let me try it again. So 900 divided by 2, that's 450. 8 squared is 64. So yeah, I get 29,000 joules. There we go. We could actually find the work done by the lifting force and the work done by the gravity. Like you could do, that is Fg times the displacement, which is 12 meters. And the work done by the cable would be 29,000 plus that. But I'm not going to do that right now. So we can use kinematics to help us find velocity or displacements if we don't know those. So there's a ton of examples there. There's quite a few questions, but a lot of them are really straightforward. They're very, very similar to these examples. So like, for instance, if you have a question and the thing doesn't move, you know right away the work is 0. So some of those questions don't take too long. All right, good luck.